forgot to email you.
Oh, yeah.
Yeah, I forgot about
Did you all get that? I gave you, and it was a simple thing to take a look at. Did you all get it? It was,
Recording stuff?
yeah.
Yeah.
All right. I just tell you today, it all comes together. You don't understand why, man. You'll have a better appreciation for the analysis and really series analysis. You're going to see how we can approximate a lot of stuff. Last time, I'll just bring this up to speed. Now, first, any questions about the home? They were straightforward. You take derivatives till you get impulses. Once you have the impulses, you do the integration and find the constants that are associated with that series, then divide it by Jn omega naught to the nth, where n is the number of derivatives you took to get there. Now you have C of n. There's one thing I didn't tell you. To get the average value, the DC value, you have to do the integration to get C0. I'll take you through this whole thing. Does anybody have a question about the homework? Now, he's seen this before. I don't know if anybody else has. All right. So let me bring you up to speed of where we're at. And it's important you follow me on this. I took a square wave, a real approximated square wave, where this is going to be T rise, tau rise, and this is T fall. As an amplitude A, it repeats itself, so it's repetitive, and repeats over a period capital T. Now, if you want to call this the pulse repetition interval for capital T, it's fine, but it's just a period. And when we have this, what we did was we said we could approximate this as a Fourier series. I took two derivatives to get Cn double prime last time, and I was in the process of getting C of n. I didn't get C of n. But in general, we're going to put that down. I have x of t is equal to the summation of n equals minus infinity to infinity of C of n times e to the jn omega naught t. Now, C of n was actually equal to 1 over the period t. Then it's divided by jn omega naught squared. This is what I was showing you last time. You all remember that? Mm-hmm. And then you had 1, then you had minus e to the minus jn omega naught tau rise. Then you had minus e to the minus jn omega naught tau. And then finally plus e to the jn omega naught quantity tau plus tau rise. And I didn't put this in here, but this is tau. And we approximate rise time and fall time by straight lines, and this is done throughout industry all the time. I'm going to tell you, you get a very accurate representation of the frequency domain spectrum and of everything else. Do y'all remember doing this?
Mm-hmm.
Is that 1 over T or 1 over tau?
Huh? What?
Is that 1 over T or 1 over tau?
This is 1 over T. And actually, you know what? And let me think about that. Oh, there is there's going to be a tau rise down here too. I'm sorry. And there's going to be an A. Because when you take the first derivative of this, you get a square wave. All right. And I mean, it goes up A over tau rise, down to A over tau rise here. I mean, basically up, down, then the derivatives will have an A over tau rise in them that when you do the integration, you'll get that. So you get down to this point, there's an A over tau rise. And now I told you, do you remember what I said the secret was? Here. I told you, anytime you see an e to the 1 minus or plus an e to the minus j n omega naught, right? And you're thinking, I'm going to turn that into either a sine or a cosine. And here you actually factor out two things. You factor out 1 minus e to the minus j n omega naught tau rise times 1 minus e to the minus j omega naught tau. Do you remember that last time? If you don't, just look at your notes. So this thing boils down to C of n equals A, and here divided by capital T tau rise. And then it's divided by, neither. It's going to be equal to A over capital T tau rise times j n omega naught squared. And then we're going to have 1 minus e to the minus j n omega naught tau rise times 1 minus e to the minus j n omega naught tau. Doesn't matter the order. If you go ahead and multiply this here, you're going to get that. Do you remember that from last time? Whether you like it or not, you do. You get it. Now I'm going to turn those into sine functions and then sinc functions, okay? And here's how I do it. Let me do it up here first. I know I'm going to have 1 minus e to the minus j n omega naught tau rise equal to e to the minus j n omega naught tau rise over 2 times e to the minus, or e to, sorry, minus j plus j n omega naught tau rise over 2 minus e to the minus j n omega naught tau rise over 2. Follow me, I just factored out an e to the minus j omega naught tau rise over 2, correct? Yeah. A lot of people don't, I mean, they don't see this very often, but you'll see the beauty of it. Now, when I do that, I can say that e to the j theta minus e to the minus j theta, right? The way it's usually put forward is over 2j is the sine of theta, right? Right? All right. So if I multiply both sides by 2j, I get this. And if I say theta is equal to n omega naught tau rise over 2, correct? I can replace that with sine theta times 2j. Do y'all see that? With me? Sure. And what do you notice happens if instead of tau rise, it's tau? It's the same thing, right? Only now it's 2j sine of n omega naught tau over 2. That's my point. So this whole, all this stuff turns into, I like doing this one time completely. A over capital T tau rise times j n omega naught squared. And then, now you'll notice I'm factoring out this half angle thing all the time, right? So out in front of this, that's a phase term. I don't really care about it yet. It's going to be e to the minus j n omega naught tau plus tau rise all over 2. That comes out in front. And then I have j2 squared, really, times the sine of n omega naught tau rise over 2 times the sine of n omega naught tau over 2. Y'all with me?
Mm-hmm.
Hang on, you'll see why I'm doing it. Some of you already know. I'm going to erase this wave so my life will be easy. I know what I'm trying. I know what this C of n has to do with. It's approximating that series with a rise time, fall time that's identical, and an on time of tau. Now, what I want to do is turn it into a sinc function. I told you before that the sinc of x, where x is just the argument, is the sine of x over x, right? So x is the argument. First argument is n omega naught tau rise over 2, right? Now take a look. Oh, by the way, do you see how I have j squared here and I have j squared there? So I'm going to get rid of the j squared. You all with me on this? I got j squared downstairs, upstairs. I get rid of that. Make my life a little easier. Now, I know I have n omega naught tau, n omega naught tau rise over 2. So I see I got tau rise, I got n omega naught. I'll put it over here. N omega naught, right? And it's tau rise. I'm almost there. I have to divide by 2, so I take one of these 2's downstairs, divide top and bottom by 2. And now I have this. So this is a perfect sync right here, correct? With me? Because the x is n omega naught tau rise over 2. You see how it appears here and here? Take a look, right? Now I need this one. Well, I got rid of one of these guys and I got rid of this, right? So I got the n omega naught. I'll put it here. Right, that's there. But I don't have a tau, so I multiply top and bottom by tau. Agreed? And then I divide top and bottom by 2. And you all see that that's really a sink of n omega naught tau rise over 2. And this is a sink of n omega naught tau over 2. Correct, class? Y'all see this? This is so important you see it. So what I'm going to do is just for the sake, my sake, I'm going to erase this and just replace it with the sink function, okay? And, you know, I'm notorious for taking shortcuts on the board, but not hopefully at the cost of your understanding. And it doesn't matter the order these appear. Okay, now this is perfect because this gives me a value of C of n that can go right in there if I want to do a double exponential series or doubly infinite series, and I replicate the square of the wave with the rise time. Matter of fact, it'll replicate exactly if you take enough terms. There are no discontinuities. Remember, the thing was continuous, and if it was discontinuous, then we have a problem. All right, now I'm going to go back and erase all this stuff. And I'll show you. Now that I got my C of n in some meaningful form here, now I'm going to take that exponential series, and I gave you this information, whether you appreciate it or not, it's another story. I'm going to turn it into just a single-sided cosine series. And there's a reason, because each one of those cosine terms is in the exact format that a phasor is. And you'll see this. Some of you, well, one of you for sure, but probably a few others have seen why we're doing it. So take this series right here, and just watch me here. You'll appreciate this. You all agree that's doubly infinite. Starts at minus infinity, goes to plus infinity, right? Now you don't need to write this down. I posted this, but you probably didn't appreciate it. By the way, you had some kind of a message, low battery or something right there.
Oh, did I?
It just went away. So this can be written as this, just follow. The summation from n equals minus infinity to minus 1 of C of n e to the j n omega naught t plus C0. When n is 0, you just have C0. That's the average value of the function. Plus, and then it's going to be a summation from equals 1 to infinity of C of n e to the j n omega naught t, right? Here I just broke it up, and there's a reason I broke it up. It's not for fun. You agree with me, class? All right. Now, matter of fact, let me put the C0 on the other side of this. And C0 was just the average value of that function, right, that I had up there. So C0 is 1 over t. Then I take the area of that function, and the area of that function was tau times A plus tau rise times A divided by capital T. So it's really going to be tau plus tau rise, and it's just that divided by T is actually times A is C0. It's just the area under the curve divided by the period T. Right?
Mhm.
When it's gone up, it has an area of 1/2 A tau rise, right?
Mhm.
And then what's going down has an area of 1/2 A tau rise, so it's 2 times 1/2, or 2 plus 2 times that, and it's equal to that. Okay, now let me go ahead and erase this, because I'm going to use this right below it. I'm trying to leave that there for a reason. Not you, Jake, but anybody else. Can you think of, if you look, why I might be doing that? Any gut feel guesses? All right? Whenever you get stuff like this, always think, how can I make this look like a sine or cosine? Boy, if one of these exponentials was negative, it sure looks like a cosine, doesn't it? Coming out there with those exponentials. Now look, you see how this goes from minus infinity to minus 1? What if we make n negative here and this positive? Follow me? All right. I mean, n was going negative, right? Well, let's make n positive and make n negative in here. Same thing, right? Isn't that right? Now, why did I do that? I'm almost there. Now take a look at C of n. C of n is equal to technically 1/t, the integral. You don't need to write this, just appreciate it. From minus t/2 to t/2 of x of t e to the minus j n omega naught t, right? Agreed? That has a magnitude and an angle. Right? Agreed? Just follow me on this. Now, if that's C of n, then C of minus n is just C of n conjugated. Because if I look at this, if I conjugate it and make that angle plus, that angle becomes negative. So it's the same thing as magnitude of C of n e to the minus j angle of C of n. That's C of minus n. All right, and you can prove this if you want. Just take a look at term by term. It does this. Sometimes, when I was sitting where you were, sometimes I do stuff like this just to convince me that maybe I didn't see everything, and then I said, okay, yeah, it works. So here, my x of t can be written as, I like to break C0 by itself, and now notice this series and this series have the same values. It goes from 1 to infinity, or from infinity to 1. The way you count doesn't matter, so I can put 1 to infinity, right? With me? Just appreciate this. So now what I do is say it's plus the summation from n equals 1 to infinity. And here, what I do is replace C of n by this, right? By those magnitude and angle. That's what C of n is, isn't it? All right, so now I say it's equal to, well, it's equal to magnitude of C of n, right? That appears here and here. And then here, it's e to the minus j angle of C of n, right? Here, it's e to the plus e to the j angle of C of n. And again, when you take this, you can obviously see, by the way, yeah, that becomes negative. And now we have that right there. Actually, let me do it this way so you can see it better. I want to make sure I really showcase this. What I'm going to do is just replace it in a series. Can you see that the first series, n equals 1 to infinity, as magnitude of C of n. Then there's e to the minus j, the angle of C of n. So it can be e to the minus j times the quantity n omega naught t plus the phase angle of C of n, right? And then it's plus the second one, magnitude of C of n, times e to the plus j n omega naught plus omega naught t, pardon, plus angle of C of n. Y'all see that? I gotta make sure you do, right? Now look, that C of n can come out in front of that, can it? Can I just take the C of n out of this one and leave it there and leave it like that? Agree? Some of you catch this. I have what now? I have e to the j theta plus e to the minus j theta. And if I divide that by 2, I get cosine theta, don't I? Right. Do you all remember that? That's Euler's. There's 3 versions of Euler's, right? There's the exponential e to the j theta is equal to cosine theta plus j sine theta. Then there's the sine theta that's equal to e to the j theta minus e to the minus j theta over 2j. And then there's the cosine theta, the one I put up. Well, you look, here the argument theta is really the argument of these exponentials. And therefore this series x of t is equal to C0 plus the summation of magnitude of C of n times 2. So it's really going to be from n equals 1 to infinity, 2 times magnitude of C of n times cosine of n omega naught t plus the phase angle of C of n. And that's what we wanted. Now remember that C of n is this C of n, but you can see the magnitude is just a times the duty cycle, a tau over 2, right? Times these sinc functions, right? And the phase is just right there, n omega naught t tau plus tau rise over 2. Y'all see that? You won't appreciate it until you see some examples of this, but now I have that. And now I go back to why I'm doing all this. So, y'all see that this is a cosine series, right? I could put n equal 1, and then I have omega naught t there. It would be a cosine variation with some phase angle and some magnitude. Then when n is equal to 2, I would have 2 omega naught. It would be at the second harmonic. When n equals 1, it's called the first harmonic, or the fundamental frequency. But what I've got here is an infinite series that's additive. And then I go back to my circuit days. I like to do it this way. So if I have something where I have some V naught cosine of omega naught t plus a phase angle, and I have a resistor R, and I have an inductor L, right? And suppose I wanted the current here. All right, good problem for if you're getting an interview. Somebody might ask you this. I've been told, actually I haven't been told explicitly by people that are interviewers, but what they do is give people tests just to make sure that their grade point average represents their knowledge base. Believe me, a lot of people come out of universities that have a high GPA and don't know what they're doing. And to me, that's terrifying because I might have been responsible for passing one of these guys. You want to make sure you really know what you're doing, all right, when you go to an interview. Get your slate, have a cup of coffee or something, come in clear-headed, because they'll ask you something like this. So how are you going to solve it? Now, a pure physicist will write a differential equation and solve. But we're engineers. We're supposed to be a little better than that. So what do? Well, y'all agree it's at a steady frequency, right? It's an AC problem. This is the AC problem of AC problems for you guys. We don't do it with a cosine. What do? We say, well, we're going to go to the phasor domain. That's V naught at an angle of theta. And we just make a note that omega naught is the frequency, right? Agree? What next? Remember, I want I. Resistance is resistance in either domain, right?
Change L to.
Right. I have to put the impedance of L. I don't care about LDIDT anymore, do I? I want the impedance. And the impedance of this is what? J omega naught L. Now this is making a little more sense. This is a real problem. They're going to ask you something like this at some point. Now I have that. How do I get I in the phasor domain? Come on. Play the game. Do we have the voltage? V naught, right? Do we have the impedance? What do we get? How do we get current? V over I, right? So we just say this is equal to V naught at whatever angle it is, right? Divided by R plus J, in this case, omega naught L, correct? You all agree with that? You all agree that's a magnitude of an angle. I don't know what the angle is or what the magnitude is. It depends on L, omega naught, and R, and V naught, and the angle theta. But I know this will have some magnitude of I naught, and it will be at an angle. You can call it angle of just theta I naught, right? It's the way it is. You all agree with that? Sure. If I give you R, L, and omega naught, you got it, right? And V naught. Now, how do I go back to the time domain? I ask this. Believe me, people, when I say this, there are people next to you, possibly, don't know how to do this. But you get asked this sometimes on a job interview where it really matters that you know what you're doing. Well, how do you go back to the time domain?
Use the cosine.
Technically, well, you're ahead of me on that, but you're right. Technically, if we take the real part of e to the j omega naught t, so whatever we suppressed over here, we bring back, and then we take this and multiply it by I phasor, or magnitude of I naught, e to the j theta of I naught, right? Now, he's ahead of you, but you can take e to the j omega naught t and add that angle to it, right? And then when I take the real part of e to the j omega naught t plus an angle, I just get the cosine of that. So this equals, this would be my I of t. My I of t actually equals magnitude of I naught, whatever that is, times the cosine of, now it's going to be omega naught t plus the phase angle. Go with me? Just to bring everybody back on board. You agree with this? That was for one term. But what if I had not just this, but I had some V1 cosine of omega 1 t plus, call it V1, that's called V0. What do I do? Well, I do the same thing again, right? Because remember, these are linear circuits, aren't they? So if you put V1 in, you get I1. You put V2 in, you get I2. If you put V1 plus V2, you get I1 plus I2. Do y'all follow me on this? All right. So with this one, I change it to this. Same deal, only now omega is omega 1, and V is V1, and the angle is now the second angle, right? Theta 1. And everything goes exactly as before. And then I say to myself, well, what if I have a pseudo-infinite series? Well, I take each one of these and I turn them into phasors. Y'all with me on this? I mean, that's a phasor, isn't it? It's just magnitude right here. It's got a cosine variation. The frequency is n omega naught t. The angle is C of n. Y'all with me? I stick that into the circuit or multiply it by the transfer function, and I get the response. All right. Now I'm going to write this down one time for you, and then I'll show you the trick of how to approximate this behavior. But I'm trying to make you appreciate this, all right? Because this is a waveform that if I gave you just that waveform there and I wanted another current, you'd be scratching your head for a while, I think. But what I'm about to show you will give you the current or anything else you want. Remember, this is for the actual C of N for that series, or that rise time, fall time square wave, realistic square wave. So now, what happens when we have a circuit? This is really MC, folks. When now I have some circuit, and I have over here, I have some X of t as my input, and it looks like anything. Doesn't matter what it looks like. I'm showing you like this. Any X of t. And this is my input. But it's got to be periodic. Or call it X of t, input. And then I have something over here, a circuit of some type. It doesn't really matter what it is. I can put a resistor, an inductor, a capacitor. I can put another inductor here. But I got some circuit, and I want to find out what V out is. Got an input, or I'll call it Y of t. I want to find out what Y of t is. Now, it doesn't matter what the circuit is. If you're going to do this problem, and you have any kind of periodic waveform, something that repeats itself, you know you can turn that into a cosine series. Y'all with me? Each one of those cosine terms can be looked at as a magnitude at an angle of the weight in front of it and the angle of the cosine at a given frequency, n omega naught, which means each one of these inductors can have an impedance of J n omega naught L, and the capacitor will have an impedance of 1 over J n omega naught C. In other words, there's an impedance associated with that, right? The X of t will be rendered as some X of not omega naught, but n omega naught in the phasor domain, okay? That's just really a magnitude and an angle. Do y'all follow me? That would be the coefficient of the cosine term, the 2c of n, and the angle. Over here, instead of a Y of t, you would have a Y of n omega naught. And then you would have something called the transfer function. It's just like from before, only now we're talking about not just omega, but n omega naught, okay? So the transfer function will be a function of n omega naught, and it's equal to Y of n omega naught over X of n omega naught. And therefore, if I wanted Y of n omega naught, you with me? That's what a transfer function is. If I want just the output, Y of n omega naught, I would take H of n omega naught times X of n omega naught. I'm just showing you the obvious. Now that's what I want, but I want it back in the time domain. All right, I'm ready to show you the whole 9 yards. All right. I can go ahead and take that cosine series and turn it into a whole bunch of phasors. And then I can multiply each one of those phasor terms of X of n omega naught by an H of n omega naught for the associated circuit. Then I can take that whole thing and turn it back into a sum of cosine of n omega naught t plus phase angle. But after you turn the crank on this is in your notes, I believe. After you turn the whole crank, if I have some X of t and I want the output Y of t, and I want to put it up here, then, not Y of n, my Y of t will be equal to my C0 times the transfer function evaluated to make equal 0. You got to do that. Plus the summation from n equal 1 to infinity of 2 times the magnitude of C of n. And the C of n, again, is going to be the associated C of n that goes with that repetitive series, all right? Times the cosine, or really, then it's going to be times H of n omega naught. Now remember, that's going to be the weight of the transfer function. It changes versus frequency. Then it's going to be times cosine of n omega naught t. It's got to have that. We're back at, now we're going to the time domain. We know we've had a repetitive series. We turn the input x of t into a cosine series. Now we feed term by term in there in the phasor domain, get the phasor domain output, the y of n, and then get it back to the actual time domain by taking the real part of each of the j n omega naught t times the phasor output y of n. And this is what comes out of it. Then it's going to be plus the phase angle associated with c of n plus the phase angle associated with h of n omega naught. And lo and behold, that is the output for any given periodic input on any given linear system where you can get an input-output relationship in the frequency domain. And here, this is fantastic stuff for engineers because everything just about you deal with are going to be linear, time-invariant systems unless you get into some nonlinear stuff that has to do with high power or transit, weird stuff, that common stuff. But that works. So, and I'll spend more time. I'm going to give you some examples of this, and I'll show you using MATLAB. If we just truncate the series, 10 values of a series for that trapezoidal waveform, all right, you can get the output for any kind of circuit very easily. Any kind of RLC circuit, not a problem. Or a differential equation, as long as it's a linear differential equation. And that's extremely valuable. Now, next, let's talk about that waveform. You'll see this. I'll show you some more applications of this. And that in a second. But this waveform here, remember what we turned it into. We turned that thing into a cosine series. If you don't remember I said this can be rendered as x of t here as some c0, which was a tau rise plus tau divided by t, capital T, the period. Some c0 plus the summation of 2 times the magnitude of Cn. In case you didn't remember, I understand. It's 2a tau over t, right? The magnitude of that the exponential, I don't care about, that's part of the phase. Then it's times the sinc of n omega naught tau over 2. And then it's times the sinc of n omega naught tau rise over 2. Let me erase this for now. And this is for n equal 1 to infinity. Are you with me? It's this times e to the j n omega naught t. Sorry. This is the time variation. This part right here is just a magnitude that varies with n omega naught. Y'all follow me on that? Just take a good look. Make sure you see what I'm doing. Now, what we like to do in EMC and in radar and in so many other areas, we like to look at worst case possibilities. Worst case means if you get by the worst case, if your system passes it, it'll pass. Everything else is better than that. So when we look at worst case analysis, here's what we do. We take a look at these values in the spectral domain or versus n omega naught. Now here's how we do it. You see this whole thing right here, you can call a constant, I'll just call this k. That's the entire coefficient at e to the j n omega naught t. Oh, you know what else I forgot? It's not e to the j n omega naught t. I'm so sorry. It's cosine of n omega naught t plus the phase angle of c of n plus the phase, just plus the phase angle of C of n, because this is just that waveform there that has the height of A. All right. But I'm going to call all of this from here to here just K. All right. Now you'll notice when I look at this, if I plot that versus frequency, just follow me. Let's plot it versus omega. And on this axis, actually what I'm going to do is going to be 20 times the log of K. All right, and usually they divide this by, I'm just going to leave it 20 times the log of K. So K here is this coefficient. Now, here it becomes important you appreciate this. When I have the sine of X over X, that's the sync waveform, right? Now you'll notice it varies as 1 over X. But it doesn't start varying until this argument right there. If you actually plot that, all right, sync of X versus X, it does this. The first 0 is when X is pi, right? Y'all remember that? If you look at this for a second, the way I'm say this in a way that's going to be meaningful to you. What you're going to see is this. When you're down here, this is going to be omega naught over 2. Just follow me on this. Or actually, that isn't going to do it. What I'm going to do is plot it versus F, and I'm going to change something to help you guys see this. I'm going to plot it versus F, but this is going to be the log of F here. And I'm going to take this series right there, and I'm going to replace omega with F naught, okay? And I'm doing this, I'm trying to do this in a way that will be most meaningful to you, so just bear with me. So first thing I'm going to do is take omega naught and replace it by 2 pi F naught. And when I do that, that coefficient K becomes 2 times magnitude of A tau over T. And then it's going to be the sync. And since omega naught is 2, so it's N pi times F naught tau times the sync of N pi, and here it's going to be F naught tau rise. You with me? Here I just replaced omega naught up there by 2 pi F naught. So there's pi's that appear here, right? Agreed?
Mm-hmm.
Now, if you look at this, I told you the first 0 appears when the sync function itself is pi, right? The argument is pi, X is pi here. So if you look at this right here, when this argument is pi, it implies that when this argument is pi right here, it would be N F naught pi tau equal pi, or N F naught tau equal 1, or N F naught equal 1 over tau. Now, let me explain the reason I'm just mentioning this stuff. I know this gets a little boring, so just hang on. Here you be attentive. What we like to do, we could show you this thing at, call it F naught, at 2F naught, at 3F naught, at 4F naught, and so forth. You all follow me? And this is going to be a log of F, so these things are not going to be linear to space. All right? Y'all with me on this? This is going to be a log in this direction, log in that. We could do that, and what we do is get this. We basically get a whole lot, if we're really low frequency, get this, and then when we hit F naught, hit this. But at some point, it would start going down. And then at another point, it would start going down, and this time at 40 dB per decade. This would be 20 dB per decade, this would be 40. So here's what we do. We don't want to do it over here. This is where it comes together. What we actually do is this. We're going to say, we're going to plot versus F. And we're going to say, we're going to let F equal NF naught, right there. But we're going to assume that this thing is going to be continuous, right? So this will be the envelope, the worst case envelope. So now if we plot the log of F here versus the magnitude here of, it's going to be times the log of magnitude of C of n times 2. This is going to be the coefficient of the actual cosine series. Times 20, we get this. We're going to get a value here that's a constant that has to do with 20 times the log of the magnitude of A tau over T. And it's going to be times 2 in here. That'll be here. The first frequency it breaks at is going to be 1 over pi tau. Now, here's what I'm saying, or pi tau. If you look at this right here, if I replace n times f naught with just f, I'm going to do this on both of these right now. Remember, nf naught is really something, replacing that by f. Here I'm taking a look at a continuous possible value where nf naught, it starts at f naught, then 2f naught, 3f naught. It's discrete. You follow me? This is going to be just taking this, making it continuous. Well, I know this one starts going down. It has its first 0, and then it starts falling off its 1 over this argument when pi f tau equals pi, right? Or yeah, that's right. And at that point, yeah, that is the point where the thing will start dropping off. It'll be the sink of 1. That's it. All right. It'll start dropping off. So it'll be 1 over pi tau. Then it'll come down at minus 20 dB per decade. Remember the Bode plots we did? It'll keep going at 20 dB per decade until you hit 1 over pi tau rise. And then it'll start going off down as 40 dB per decade. Now, why am I saying that? Because now that I have this, if I want to know the output of a circuit for an input with a trapezoidal input, I can go ahead and I can find out where I am here, and I can use that as my input. I can basically use that as the input and get the output based on it. Let me show you some examples of this because I'm aware of the time, and until I show you some examples, you won't appreciate this. I don't think. But this is stuff that I'm thinking about 3 or 4 things I could mention here. Remember this waveform right here. So I'm going to do some problems, and you'll see it. Remember, we're going to use that one, that thing right there. That's the Cn value, and that's for a trapezoidal wave. That's how you get it. So, I've got plenty of problems on this I got upstairs. I'm going to take one out of here, though. this is a problem you'll get. So suppose, again, this is going to be a repetitive trapezoidal waveform in the input, and it has this. And this is going to go right into the frequency domain so you can see it. This is going to be the sketch of the actual input's magnitude and frequency domain. So it's magnitude of x of omega here. And this is going to be 120 dB microvolts. I'm going to get to that in a second. It's going to stay 0. This is going to be a log of plot. Here it's going to be a log of omega. It's going to stay 0 dB. This is going to be 0 dB until it hits omega 1 is 10. So this is a log of omega. Then it's going to come down at minus 20 dB per decade until it hits omega 2, and that's equal to 20 times 10 to the 6th. Oh, this is 10 to the 6th is the first one. And then it starts falling at minus 40 dB per decade. And this is an approximation of the envelope. And they have a linear system here, so they have some input, x of omega, and they have some output, y of omega. But what they're doing is they're showing you the output relationship to the input in the frequency domain. And here, this is going to be versus omega, and this is going to be a magnitude of h of omega. And they got a straight line plot of plus 20 dB per decade right here, and it starts at minus 30 dBs. Here's the reason I did this problem. I've just told you that you can take a square wave and turn it into this. I didn't want to go ahead and draw the square wave and get this from there. I'm just giving you this as the envelope of the cosine wave. It's really the worst case possibility for the values of the magnitude. How did I get this? Well, normally when they plot this axis, this is 20 times the log of 2 times A times tau over T. But when you see dB microvolts, it means it's normalized to a microvolt, or that this is divided by 10 to the minus 6. That's dB microvolts. You with me? That's all it is. Now, here, you can see that this thing is flat until it hits 10 to the 6th. Then it starts going down to 20 dB per decade until we hit this point, which is 20 megahertz. Omega's not 20 meg, 20 megaradians per second. Then it starts going down to 40 dB. But you can see this is continually going up at 20 dB per decade. And what they want us to do is, what I want you to do is show me graphically what happens based on that plot for the output. And then an exact value. So I'll draw this over here. So take a look at this. It says the output at, I don't know what that first part is. Well, it's 0 dB until I hit omega 1. And this one actually starts at 10 to the 5th. So let's start at 10 to the 5th here. It's going to be a logarithmic horizontal axis. So it's really the log of omega I'm plotting. But at 10 to the 5th, right here, now take a look. This thing's just 0 dB of change, all things, but it's got 120 dB microvolts it starts at. You with me? I want to make sure you all are. So if I take that, and then I got 30 dB of loss, so it's 120 minus 30, or it's 90 dB, agreed? So if this is 10 to the 5th, It starts at 90 dB microvolts. Now you see that slope is a constant 20 dB. So between 10 to the 5th and 10 to the 6th right here, that's 1 decade, right? 20 dB per decade would mean it increases by 20 dB. Y'all with me on this, class? So it goes up. It's going up at a constant rate because of this thing. So it's going up. And when I hit 10 to the 6th, then I come up here, and I know that's 110 dB microvolts. This is how this works. All right, this is how it works. What that is probably an inductor right there in series with the capacitor. Don't worry about that part. I'm in series with the resistor. Now it hits this point at 10 to the 6th. Then it starts going down at 20 dB per decade. You all see that? Well, it was going up at 20 dB and it's going down means zip. It doesn't change. You all follow me? So it's going to be flat. Until I hit 20 times 10 to the 6th, right? Now this is a drawn scale by any means, but you follow me. So when I hit this, and this would be logarithmic, 20 times 10 to the 6th. Then what happens after that? Go down at a rate of 20 dB. Y'all follow me? So if I wanted this anywhere, and I'm just going to show you it anywhere. All right? Now listen carefully. This is how you do it. This is an extrapolation. Suppose, I know it peaks at 110, right? Suppose I wanted the value out here at, say, 100 times 10 to the 6th radians. I want to know what the value is out here. How do you do that? Now, this is a good fundamental question. You'll get it if you're sharp, maybe not right now, though, because you're probably tired of this stuff. Just level with you guys. I sat where you were once. I know at the end of an hour and 15-minute lecture with something abstract as this, I'd be staring at the guy like, give me a moment. Don't ask that. All right, here's how you get it. We know where it is at 20, right? All right, if I want to know what it is at this point right here, here's how to get it. I start with the known point. So I can say this point will be equal to, I'll start with 110 dB microvolts. And then it's going down at a rate at 20 dB per decade. Follow me? So you take the frequency you started at, right here, as the bottom frequency. It's going to be a ratio of the two. Down here, that's 20 times 10 to the 6th. Up here, it's 100 times 10 to the 6th. And that will be the value. Y'all follow me on that? Mm-hmm. Now, believe it or not, you would have got it, but you would have been scratching your head for a little bit. Here's the beautiful thing about it. I mean, I put that down. It's actually a log. It's log of, this is log base 10 of the upper frequency, which is 100 times 10 to the 6th, over the lower frequency, which is 20 times 10 to the 6th. This is log of that. Sorry, I didn't put it down.
Why is it log again?
Because this is going to be, it's 20 dB per decade, right? And when you're plotting, that's a logarithm. So just think about it. If it's 20 dB per decade, if this frequency is 10 times this frequency, it would be the log of 10. All right, log of 10 is going to be 20 dB. If this frequency was 100, and this frequency was 1, then it would be 20 times the log of 100. That's 2 decades, and that would be 2, so it would be 2 times 20 or 40. Y'all follow me? This works perfect. That's the easy way to do it. So this value would be what? 20 times log of 5 is, I'm not sure what that is, but you have to subtract that from 1/10. That's how you get this. You with me? This is real important. Now here, I circumvent all that values from the square wave to get all this stuff. Because frankly, most of the time in the real world, we don't use that. The only thing we look at is the rise time and the duty cycle. And from there, we create this plot. once we have that plot, usually it's an F, not a mega, but once we have that plot right there, game over. All right, because then no matter what the transfer function is, we can just find out what the transfer function is like I did over here, and I can get the output very easily, and you'll see this. So next, this ends at 2:30, okay. So now I'm going to do one, and this time we're going to do the whole problem without the help of just taking and turning into a graphical thing right off the bat. By the way, has anybody worked out there with real spectral analyzers or network analyzers anywhere? You work with radar, huh?
They have them, but I have not.
If you're going to find out what I'm showing you has a direct application of real, and if you work with a spectral analyzer, you'll see this stuff all the time. Network analyzers too. I'm telling you, oscilloscopes, no. You see a square wave, but when you're doing something where you get the frequency domain stuff, what I'm showing you is this is directly applicable to most instruments. So now, what I'm going to do, and I want to replicate this, I'm good. I don't know if there's another class or not coming in. Wentworth's book had virtually one word on bandwidth. Now you're getting the real way to analyze things in frequency. I don't even use bandwidth when you have anything with a rise time, fall time, and a duty cycle. It's meaningless. I mean, in a sense, yeah, people argue, well, yeah, it gives you an approximate idea. Not really. All right, here I'm going to take a circuit and want to tell you one other thing too. Almost all real world circuitry, like your laptops, your phones, real radar installations, they run on digital clocks. Everything they deal with are digital circuitry, are digital signals that they have to analyze in the spectral domain. Now, it's true that with the radar, you are feeding that at a high frequency continuous signal. But the truth is, in this day and age, even that signal is ripped apart in the frequency domain with Fourier series analysis, or just Fourier analysis to get all this information that you'll find useful. Here, we're going to not have a continuous time signal. We're going to have a clock. And the usual symbol for a clock is just this. They'll have something like that inside there. It's a clock. They're going to have a circuit that has 70 picofarads here. And here it says, back to this clock, it's got a 0 to 5 volt cycle. And the rise time, fall time, so tau rise is equal to 20 nanoseconds. And it's got a 50% duty cycle. So 0.5 is equal to tau over t. Remember, tau is the on time. Capital T is the period, so it's got a 50% duty cycle. And they want the levels, so they want the output here. They want plus to minus the value of the 11th harmonic. So what is the 11th harmonic? It's when n is equal to 11. Remember, the magnitude of that is 2 times C of n. So here's how we do this one. You're going to be surprised how easy it is. I've got, need a fundamental frequency. For this one, the fundamental frequency is 10 megahertz. So bear with me, make sure you get this down. I have F naught is equal to 10 megahertz, okay? Now, what I'm going to do is draw the spectrum, the envelope, you might say, of that 2 magnitude of Cm, continuous time. That's the key. So what I do is first, I've got the rise time, thank God. Now I need tau. So tau is equal to 1/2 t, right? How do I get t? Look at this. 1 over 10 megahertz or 1 over 10 to the 7th is 10 to the minus 7. Do you agree?
Mm-hmm.
So this is 10 to the minus 7, right? Or what? 100 nanoseconds. Agree? You agree with that? That's 10 to the minus 7? All right. So now I draw, I'm going to do dB microvolts. I'm going to put log of F. Here I'm going to use F. And on this axis, I start with, or this is going to be 20 times the log. This is going to be my starting point of 2 times a tau over t, or the duty cycle. And just look at this for a second. Oh, I've got to divide this by 10 to the minus 6 because it's going to be dB microvolts. Now look at this for a second. This is a nice thing about a duty cycle of 50%. I have 0.5 is t over tau, right? T over capital T. Tau over t, pardon, tau over t. Do I need to write this bigger? This is going to be on this axis 20 times the log of the magnitude of 2a tau over t divided by 10 to the minus 6. Now take a look at this. See how tau over t is 1/2? 1/2 times 2 is 1, right? Y'all with me? Tau over t is 50% or 1/2. And that means it's really, A is 5, right? That's the magnitude it goes to. So this is really 5 over 10 to the minus 6 in dB microvolts. So this is going to be 5 over 10 to the minus 6. So really 5 times 10 to the 6. Got to take the log of it times 20. Can anybody give that to me? That's where we started. We're going to stay there. And this is the log F here, until we hit 1 over pi tau. And then we're going to start coming down. Actually, that's too fast. Start coming down at minus 20 dB per decade until we hit 1 over pi tau rise. And then we come down by minus 40 dB per decade. So, just tell me what that is.
134.
All right, so this is 134 dB microvolts, and that's what it is till you hit a low frequency. You with me? Now it stays there, and then tell me what 1 over pi tau is. So tau is 10 to the minus 7th. So that's 1 over pi times 10 to the 7th here.
Did you have t right there?
Huh?
Isn't that supposed to be half?
This is, if I take 1/2, see this, yeah, you're right. You're absolutely right. That's 10 to the 7th. 1 over this 10 to the minus 7th, divide by 2, I'm sorry. So it's 5 times 10 to the minus 8. My bad, not 100 nanoseconds. My bad. This is going to be 5 times 10 to the minus 8, or 50 nanoseconds. My bad. Thank you very much. You agree with that? So what is 1 over pi times 50 times 10 to the minus 8, or 50 nanoseconds? What is this?
6.4 times 10 to the 6.
I think it's 6.36, but
Yeah. Yeah, I just rounded. 6.366.
times 10 to the sixth, right? Right?
Yes.
6.36 megahertz.
Yep.
Now what's this? 1 over pi tau rise is 20 nanosecond.
Sorry.
This will be, when we're done with this, you guys can go.
20 nanoseconds. I did that wrong. I did
1
that
over
wrong.
pi times 20 times 10 to the minus 9.
1.59 times 10 to the 7th.
15.9 megahertz. All right, so this one is 15.9 megahertz. Right? They want the value of the 11th harmonic. Listen to me now. That's 15. Let's see where we are out here. We're just going to read it from the chart. I mean, we're going to find that value here, and then we got to get the transfer function. Let's just find the value here, all right? Follow me. So the fundamental is 10 megahertz. What would the 11th harmonic be if this is the first? 110 megahertz, right? It's 11 times that, right? 11 times 10 megahertz, right, is going to be 110 megahertz. So I'm out here. I'm way out here, right? That's 110 megahertz, all right? So now, I mean, that's what the signal is. Do you all agree with this? So if we're at 110 megahertz, just the input signal strength right here, right, would be what? Well, look, I started with 134, so this is going to be what the input value would be. I'll just call it 11th harmonic strength. It has a value, start there, 134. That's dB microvolts, right? Just follow. Now I subtract off minus 20 dB per decade times the log of what? The upper frequency here is 15.9 megahertz. The low frequency is 6.3 megahertz cancel. 36 megahertz, right? That brings me to here. How do I get to the 11th harmonic? Now I'm going to try minus 40, right? Because the slope is minus 40 then, right? Minus 40 times the log of what?
110.
Right. 110 megahertz divided by
15.9.
15.9. And that's going to be the value in dB of the input, right? You agree with me? Just give that to me. I'll let you go after this. Bear with me, please. I'm really trying my best to finish this point. This is going to be the magnitude of the input. So it's 20 times the log of the magnitude of 2, magnitude of A times tau over T. Only now it's going to be, I'll just leave this alone. It's going to be the magnitude of 2 magnitude of C of n over 10 to the minus 6, where n is 11, and just leave it at that. But what do you get for that when you do this? 134 minus 20 log of 15.9 over 6.36, and then minus 40 times the log of 110 over 15.9. I can't do that one in my head. And very few people can. I had a guy with a slide rule years ago. He was a physics teacher. That dude it's amazing how he could do logs that he could just, oh, that's what it is. Faster than a calculator.
Got 92.
Is that what you got?
That's also I'm getting.
92.4 dB microvolts. All right. Now, the final part, they want the output, right? So just watch. Of the 11th harmonic, right? We got the input. Now we need the output. The 11th harmonic is 110 megahertz, right?
Mm-hmm.
So follow me on this. The transfer function of this, just input output, H of, and I'll just call it H of N F naught, doesn't matter, I can call it N omega naught. Well, the transfer function is this over this plus this, right? So that's really going to be 1 over J omega C over 1 over J omega C plus R. Bear with me on this. I'll multiply top and bottom by J omega C. I get 1 over 1 plus J omega R times C. Y'all with me on that? I get that. Now omega has got to represent the 11th harmonic, correct? That's 2 pi, so this is equal to, just watch me now. That's 1 over 1 plus J times omega, which is 2 pi. The 11th harmonic is 110 times 10 to the 6th, right? Times R, which is 100. Let me try to make this a little bigger. So this is equal to 1 over 1 plus J 2 pi, and this is going to be 110 times 10 to the 6th, and then it's times R 100, 10 squared, times C, which is 70 times 10 to the minus 12. Y'all with me on this? All right, now let's just see this for a second. I got 10 to the 6th times 10 squared is 10 to the 8th, right? Then I have 70 times, or 70 is 7 times 10, so this is 9th, right? And that means that's going to be minus 3. What I'm trying to do is get this down. So it's minus 3, that's 1.1 times 10 squared, and so that's going to be 10 to the minus 1 times 7. When you do the whole thing on this, you're going to get something, right? I just erased everything, but when you do it, you're going to get something. Here. Y'all know that works, right? I'm running out of room. Just do this. Give me the magnitude of this. 1 over 1 plus J. It's going to be 2 pi times 110 times 10 to the 6th times R is 100 times C is 70 times 10 to the minus. And that's P, right? So it's minus 12. So what's the magnitude of this? I don't really care about.
The angle. Magnitude is 0.823.
Is that, did you confirm it?
Oh, do it again,
The key is right here. What's the value right there? I'm looking at that. That's 10 to the 8th, 10 to the minus 12 is 10 to the minus 4, 10 to the minus 3, 2, 1, 10 to the minus 1, 7 times 1.1 times 2 pi times 10 to the minus 1. I can't do that in my head. Can you tell me? Just give me this coefficient here. What's that?
Let me type in stuff. 5, 10,
Don't sue me, please.
12.
What?
I got 4.8.
As a coefficient?
The coefficient.
I mean, is the whole thing?
No, for J.
Just as coefficient of J? Let's run with that. All right, square that value and add 1 to it and take the square root. It's going to be about 4.9, maybe 5, right? Because I want the magnitude. It's about 1/5, so it's about 0.25, right? Or, so 0.2.
Yeah.
About 0.2?
0.2.
All right, 0.2 is H, right?
0.22. I got it.
Now take,
I used a simplified one. I don't think that was. We did that right.
now take 20 times the log of that. 20 times the log of 0.2.
Negative 13.9.
Minus 13.9, right? Now subtract that from 92.4, right? And I'll tell you what the answer is. 78.56, is that what we get?
78.02.
And guess what? 78.56 dB here.
Okay.
All right, that's how you do a problem like that. And I know, it was late, and I ran you about 9 minutes over. So I owe you time, but I started late.
You have to give us a hint for the quiz. Means you have to give us a hint for the quiz, right?
Yeah, absolutely. I'm
That
gonna
sounds
give you
great.